Find an example of a series such that the individual terms go to 0, but the entire series diverges. Well, this is such a well-known example that we've been using so many times. So here, this one diverges because it's a harmonic series. Or another way to say it would be P series with P equal to 1, so diverges. But if you take the individual terms, you get 0. And this is counterintuitive because you're adding things that are getting smaller and smaller, yet it's getting smaller and smaller to 0, yet the entire thing diverges to infinity. So that's kind of hard to understand how that can be. So this is a very important example that you should remember. Okay, well, what about this one? It says you have individual terms going to 0 like before, but now it has to be alternating. So what kind of series would do that? Now the thing is, series like this one wouldn't do because we know that this example is an example where it converges conditionally. If you take the absolute value, it doesn't converge, but because of the alternating series test, this actually converges, right? So we scratch this out. So and then think about what could be the right one. Now, if you read this condition carefully, you see that already one of the alternating series test condition is there. This is, as you can see, this one is one of the conditions which is says limit an has to be 0, and number 2, an should be bigger than an plus 1. So these two conditions together give you that alternating series test implies the convergence of this series, at least conditionally. And since only one of them is supplied, that means this one has to be violated somehow. You have to think about a sequence where it's not decreasing yet still goes to 0. So what kind of sequence would do that? Well, here's the idea. If you have 1 over 1 minus 1 over 1 plus 1 over 2 minus 1 over 2 squared plus 1 over 3 minus 1 over 4 squared, sorry, 3 squared I meant, plus 1 over 4 minus 1 over 4 squared, and so on and so on. This is an alternating sequence series, right? You have plus minus plus minus plus minus plus minus. So definitely this is an alternating sequence. We know that it's going to diverge to infinity because 1 over 2, 1 over 3, 1 over 4, the positive ones are like 1 over n, and the negative ones are like 1 over n squared, and therefore this one is going to infinity, whereas this one is a finite number, so it's infinity minus some finite value, which is infinity. So this definitely diverges. And another thing that we see is that this violates the second condition because it's 1 over 2 is less than 1 over 1, but over here 1/3 is bigger than 1 over 4. So it doesn't satisfy this condition. That's why it manages to be an alternating series and yet goes to infinity. So that you can write this out, or if you want to write this as a formal sequence, then it's a little bit tricky to do. You say an is equal to, well, if n is odd, then we're going to do 1 over 2, no, you're going to do n minus 1, actually n plus 1 divided by 2. 1 over n plus 1 divided by 2. So when n is 1, it will be 1 plus 1 over 2, which is 1, so you're going to get 1 over 1. Okay. If n is even, then we will write n over 2 squared. Okay, so when n is odd, you get 1 over n, and when n is even, you get 1 over n squared. You can see that if you try n equals to 1, 2, 3, 4, 5, and check it against this series here, you're going to see that that actually does work. Alright. Find an example of a series where you do have a decreasing function, but it diverges. Well, to be decreasing but still diverging, of the two conditions for alternating series test, limit an going to 0 and then an bigger than an plus 1. This one's okay, but this is not yet okay, so this one should be violated. How do you make this not work? Well, think about something that goes to 1, for example. So think about an equals to, say, 1 plus 1 over n. Now this definitely is bigger than 1 plus 1 over n plus 1, which is n plus 1. So it does satisfy this condition. Check. But since limit an is a limit of n going to infinity of 1 plus 1 over n, and this goes to 0, you're going to get 1. And that's not equal to 0, therefore diverges by test for divergence. I mean the nth term test for divergence. Okay, find an example of a series such that this is true and it diverges. And number 10, it says this is true and it converges. Basically, what it's asking for you to do is it wants to show that when this r equals to limit n going to infinity of an plus 1 over an, when this gives you 1 or negative 1, then the ratio test doesn't say anything because it could be either way. It could be diverging or it could be converging. And for the diverging case would be just 1 over n diverges, and limit n going to infinity of an plus 1 over an would be limit n going to infinity of 1 over n plus 1 over 1 over n, which is limit n going to infinity n over n plus 1, which is 1, just as what is required. Okay, so that's the right answer. Sum of 1 over n is an example that satisfies all the requirements. Here, you try sigma 1 over n squared. Right. This one converges by p-test. And we know that limit n going to infinity of an plus 1 over an is limit n going to infinity of 1 over n plus 1 squared divided by 1 over n squared, which is limit n going to infinity of n over n plus 1 squared, which is 1. Okay, so it satisfies everything while being convergent. So 9 and 10 shows that when this limit becomes 1, that means ratio test is useless. Is useless. That means you have to resort to other tests. There are many others, right? The direct comparison, limit comparison, the integral test, test for divergence, alternating series test. There are many tests that you can use that's not ratio test. Find an example of a convergent series where ANs are positive and this AN diverges. In other words, what you want to show is that find an example of a series which converges conditionally. That's what it's asking you to find. It doesn't converge if you take the alternating signs away, but it itself converges. Well, that's very well known too. You should know this. This one converges by AST because limit 1 over n is 0, right? And also limit n going to infinity. Also 1 over n is less than 1 over n plus 1. So this means that an is bigger than an plus 1. So by these two conditions, we know that this converges by AST, but sigma of 1 over n, when you take the absolute value, diverges because harmonic series. Okay, what's the error bound for this partial sum? Basically, here's how you think about the alternating series. Alternating series, when you start with something positive, when n is 1, you get what? 1 over 2. That's the first one. So let's say this is 1/2. So you add 1/2, so you go to this way. And then from here, the next number is, if you plug in 2, you get 1/8. So 1/8 is a small step on the negative. Since it's negative, it's negative 1/8. So when you add the first term, you're at 1/2, and then you add negative 1/8, you're here. And then the next one, what's that? 1 over 18th, so you're here. So if you add alternating series, you always go back and forth while the step sizes become smaller and smaller. That's what it means to be converging through alternating series test, because alternating series test has this condition that the next term is smaller than the previous one, okay, because of that. Now, what that means is that when you take a jump, you know that the actual value, the true value that the sum is trying to approximate to, when you take a jump, see, when you go back and forth, when you take a jump, eventually you're gonna end up somewhere here. I don't know exactly where, but there is this actual target point. The true limit value is somewhere here, right? So if we say there's a true value, then the alternating series always passes them by. So it goes passes them by, passes it by, passes it by. So that's how it works. So your error value will be always less than the distance of the jump of the next one. So what I'm trying to say is that if I have S of 99, if you add S of 99 means A1 plus A2 plus all the way up till A99. This and the actual value, true value T, would be less than the next one, A100. So your error will be determined by A100. That's what it means. Oh, actually, this is an alternating series, so I should be saying A1 minus A2 plus A3, and then let's see, it's plus A99. So if you have this plus minus plus minus plus and so on, then the next term will give you the error size. So what is A100 in this case? A100 is that's the absolute value of this one, which is 1 over 2 and then 100 squared, and that's equal to 1 over 2 times 10,000, which is, what's that, 0, well, you can just write it as 20,000. So that's the error bound. This is actually the error bound. If you want decimals, this will be 0.00000, let's see, 10,000, 05. Okay, so that will be the error. That means this summation will be very, if you compute this to the 99th term, then you can be sure that the 4 decimal digits are correct. Okay, so that's your error bound. for each sequence, these are limits of the sequence. What do you get? Limit ln of n plus 2 over n plus 1. Well, this is the dominating term, so it's ln of 1, which is 0. That was easy. B, negative 1 to the nth power. Well, this just alternates between, this will become like 1, negative 1, 1, negative 1, positive 1, negative 1, positive 1. If you plug in 1, when n is 1, it's going to be negative 1. When n is 2, it's going to be positive 1. When n is 3, it's going to be negative 1. And it just alternates between these two values, so this does not exist. Okay. C, limit 1 plus 1 over n to the n. Well, we've done this many times before, so you probably know what to do. X is 1 over n. So this is limit x going to 0 plus and 1 plus x. Since x is 1 over n, that means n is 1 over x. So you get 1 over x, and then you do the e to the ln trick, right? ln of 1 plus x, 1 over x, that hops over the log limit, then limit n going to infinity, e to the ln of 1 plus x over x, differentiate top and bottom, and that's going to give you limit n going to infinity of, this is x going to 0, right? So I should have written down 0 plus. Okay, this is 0 over 0 type when x is 0, so we can use the L'Hopital's, and using L'Hopital's we get 1 over 1 plus x over 1, and this is really x going to 0. When x is sent to 0, you get e to the 1 over 1 plus 0, which is just e. So it converges. Okay, and then this last one, d, well, that's really easy. Limit n going to infinity, 2n squared minus 7 over 8n to the 5th minus 3. Well, these are the dominating terms, but because n to the 5th is much bigger than n squared, it's just going to be 0. So these were really simple questions. But the reason I have these questions is because I want to let you be aware of the difference between limit of the sequence and the limit of series. So these are sequences, not series. Okay, number 14. Find the interval of convergence and radius of convergence of the following power series. Okay, so let's try that first. How do you do interval convergence? Basically, what you do is you do the ratio test, right? Limit n going to infinity. You just copy whatever that's there down here, and on top you put 2n plus 3 because n is replaced by n plus 1, and on top you have x to the 2n plus 3. Okay, and that is going to be 2n plus 1. Say outside is on the top, so these two multiply, over these two multiply 2n plus 3 over x to the 2n plus 1. And you're sending limit n going to infinity. Now x of 2n will cancel away, and x cubed divided by x would be x squared. And also this one, when n is sent to infinity, 2n over 2n is 1, so it will be like 1 times x squared. So that's going to be x squared. And that means that when x squared is less than 1 and bigger than negative 1, this series will converge. Now, x squared is always positive, right? So this condition actually doesn't say anything. And for x squared to be less than 1, that means x has to be less than 1, but bigger than negative 1. If x is negative 2, you know that it's going to be positive 4, so it's going to violate this. So for x squared to be less than 1, we know that x has to be between negative 1 and 1. So that is well, first of all, the radius of convergence is half of this interval. From negative 1 to 1, radius of convergence is from 0 to 1. So radius of convergence is equal to 1. Whereas if you look at this, you need the interval of convergence. Now that's a different matter. If x squared is actually equal to 1, which is a case for x equal to 1 or x equal to -1, in that case you may have to figure out each of these separately, because the ratio test is silent on what happens when x is equal to 1. We know that when x is bigger than 1, it definitely diverges, but when x is 1 or -1, when x squared is 1, which means when r is 1, then you don't know if it's going to converge or diverge. So that case has to be dealt separately. Okay, so first, x equal to 1 is sigma n equal to 0 to infinity. Since 1 is plugged in here, 1 to 2n plus 1 is just 1. And that's infinity because it's a harmonic series. Remember, harmonic series is some constant over an plus b. So that's a harmonic series. And also for x equals to -1, it will be n equal to 0 to infinity. And since -1 to 2n plus 1 is an odd number, see, 2n is an even number. 1 more than an even number is an odd number. So 2n plus 1 will always give you an odd number. And if you take the odd power of -1, it's always going to be -1. So the top will just be -1. And that's again harmonic series, so it's going to be -infinity harmonic series. So that means none of the 1 or -1 is contained in the interval of convergence. So we have interval of convergence as the open interval from -1 to 1. Now you have to always check the endpoints, because sometimes at the endpoints you do get a finite value that does converge. Okay, so the answer is that radius of convergence is 1, and interval of convergence is from -1 to 1. Okay, now part B. What is the derivative of this function? Well, derivative is just simply derivative. You just take the derivative. If I differentiate, that's going to be 2n plus 1 times x to the 2n, because this number hops in front and you subtract 1 and divide by 2n plus 1. So these two cancel and you get sigma of n equals to 0 to x to the 2n. Okay, now part C. Identify the function whose Maclaurin series is a power series shown in A. Okay, so what kind of power series, what kind of function will have Maclaurin series exactly equal to this? Well, part B is a hint. See, this one is a very simple summation. If you write them out, when n is 0, you get 1, because anything to the 0th power is 1, plus, when n is 1, you get x squared. When n is 2, you get x to the 4th. When n is 3, you get x to the 6th, so on and so on. And as you can see, it's a geometric series with common ratio x squared. Every time you move to the next one, it's multiplied by x squared. X to the 4th times x squared, you get x to the 6th. So we use the formula a over 1 minus r, which a is the very first term, which is 1, and 1 minus r, where r is your x squared. Okay, so that is what we have. But this is not the original thing. This is the derivative. So what we are looking for is, we are looking for a function, this mysterious function, whose derivative is 1 over 1 minus x squared. Okay, what could that be? Well, that means f of x is the integral of 1 over 1 minus x squared. And since this one can be factored, when the denominator can be factored, you actually have to do partial fraction expansion. So we do the partial fraction expansion. You're supposed to put a and b and then you solve, but at the end, let's see, 1 plus x. Yeah, so if you add these, you're just going to get 2 over 1 minus x times 1 plus x. You can see that. So it'll be just 1/2 of this. See, if you add them, it will be 1 plus x over this side, 1 minus x over that side. 1 plus x plus 1 minus x will be 2. So you're going to get 2 over 1 minus x times 1 plus x when you combine these two fractions into 1. So putting a 1/2 will cancel it. So these are the same algebraically, which means this is 1/2 ln of 1 minus x and plus 1/2 ln of 1 plus x. I didn't put absolute values here because we know from the first one that x is between 1 and -1. So since x is less than 1, this will always be positive. So there's no need for any absolute value here. And don't forget plus c. Now, how do you know what should be the value of c? Well, think about this. What is f of 0? If I say f of x is this thing, what's f of 0? That's when n is 0, you have x. When n is 1, you have x cubed. So everything has x attached to this. So when you plug in 0, all these x's will just vanish away. So you're just going to get f of 0 equal to 0. Now, if you're not so sure of why that's so, you can actually write this explicitly. Well, the first term is x over 1. The next term is x cubed over 3 plus x to the 5th over 5. So that's the sum. If you write it down explicitly, when you plug in 0, every one of these have x in there. So when you plug in 0, it's going to give you 0. So you need a c which will make the entire thing 0 when x is 0. But when you plug in 0 here, ln of 1 is 0, ln of 1 is 0. So that means c should be 0 too. So we see that f of x satisfies all the conditions, the fact that the derivative should be equal to 1 over 1 minus x squared, and the fact that f of 0 should be 0, if we let c equal to 0, and the answer is so that's the answer for c. Okay, and then this one right here, this is the answer for b. Okay, find the interval of convergence and radius of convergence of the following series. Okay, always start with the ratio test. So you have -1 to the n, 2n plus 1, x minus 3. Just copy this in the denominator and then you raise this by 1. And then x minus 3 and plus 1. So that if you divide, it will be -1 on top. This divided by this will give you 1x minus 3 there. And then if you divide, this is 2n plus 3. So it will be 2n plus 3 down here, and there will be 2n plus 1 down here. So this is what you're going to get if you simplify it. And since this is just going to give you 1, see, when n is really large, 1 and 3 can be just neglected, ignored. And then you have 2n over 2n, and you get 1. So you get negative of x minus 3 as your result. Therefore, for this to converge, you need negative x minus 3 to be between 1 and -1. Which means that if I multiply by negative, x minus 3 should be between still -1 and 1. Right? So multiplying negative to 1 will give you -1, but this inequality will flip, so it's going to give you this. Multiplying -1 to -1 will be +1, so this inequality will flip, and you'll get that. Right, so what I'm trying to say is that negative x minus 3 less than 1. If you multiply -1, then it gives you x minus 3 bigger than -1, which is same as this part. And you write this and multiply -1, you're going to get this. Okay, now you add 3, which gives you 4 here and 2 there. Okay, so we know that inside the interval 2 to 4, definitely this converges, and since this interval has length 2, radius would be 1. So radius of convergence is 1. For the actual interval of convergence, we have to check for the 2 endpoints. When you have x equals to 2, then we have sigma n equals to 0 to infinity, negative 1 to the nth power, 2n plus 1, 2 minus 3 is negative 1, and if you have negative 1 to the nth times negative 1 to the nth, that's negative 1 to the 2nth power, but that means you're taking even powers of negative 1, which is just 1. So this is 1 over 2n plus 1 that diverges because it's a harmonic series. And then when x is equal to 4, this time you get sigma n equals to 0 to infinity. When you plug in 4, 4 minus 3 is 1, so 1 to the n doesn't do anything. So you simply have negative 1 to the n over 2n plus 1. Now this one converges by alternating series test because limit of 1 over 2n plus 1 is 2n plus 1 is equal to 0. And also 1 over 2n plus 1 is definitely bigger than 1 over 2n plus 1 plus 1, which is the an plus 1. Okay, so therefore, since x equal to 4 does converge and 2 does not, the interval of convergence is 2 is not included, but 4 is included. So that's the final answer. Okay, let's write out the first 3 terms of the series. When n is 0, you get 128 over 2 to the 0th of x to the 0. When n is 1, you get 2 to the 1 down here and x to the 1 plus 128 over 2 squared x squared. Okay, and since anything to 0th power is just 0, anything to 0th power is 1, you get 128 plus 64x plus 128 divided by 4 will be 32 x squared, and so on and so on. Okay, now from this we can find f of 0. Why? Because everything has 0 in there, so it'll be 128 plus 64 times 0, 32 times 0 squared, and so on and so on. So everything here is 0, so you just end up with 128. What about f prime of 0? Well, first you differentiate this. 120 will just go away. You're going to get 64 plus 64x plus something something. Right? That's what you get if you differentiate these, and then you're setting x equal to 0, so it's going to give you 64 because everything afterwards is going to vanish. How about f double prime? Well, if you differentiate again, then this one will become 64. So, and the other ones that have x squared in there is going to come and give you something times x, and so on. When you plug in 0 in there, then you're just going to get 64 by itself. So the answer will be 128, 64, and 64. Let's think about the last question. If you consider this as a geometric series, you can find an explicit formula for f of x. Well, is that really a geometric series? Let's see. We had 128 as the first one, and then the next one was 128 over 2 times x. The next one was 120 over 2 squared times x squared. Oh, so you can see that this thing, when you write them out explicitly, every time you move to the next one, you multiply 2 over x, right? X over 2. X over 2 is being multiplied to get the next one. So your r is x over 2, whereas your a is the very first one. That's your a. So if you use the formula a over 1 minus r, it's going to be 128 divided by 1 minus x over 2. Okay, so that's the explicit formula. This is our f of x. Now, when is it valid? It's valid when x over 2 is between 1 and negative 1. That's when geometric series is actually gives you the definite convergence, right? If this is not true, it always diverges. Even the endpoints diverges. When x over 2 is equal to 1 or x over 2 is equal to -1, the geometric series diverges. Yeah. That's something that's different from the ratio test or root test. So you have to know that distinction. Okay, so this is the condition. Therefore, if you multiply by 2, you get -2 to 2. So this is true when this is true. Okay, the following function is called a Bessel function of order 1, which is pretty important in spherical functions. So if you try to solve any engineering mathematics that deals with spheres, you're going to see these Bessel functions appearing. It says write down the first 3 terms of the sum. Well, that's easy. You just write down -1 to the 0th power, 0 factorial, 1 factorial, and x over 2 to the 0 plus 1. So it's like that. Okay, so, and then plus -1 to the first power over 1 factorial and 2 factorial x over 2 to the 3rd power plus -1 to the 2nd power 2 factorial, 3 factorial, and x over 2, and then you get 5. Okay, so we have this, and then 0th power will be 1. You should know that 0 factorial is always 1. That's just by convention. Many formulas become horrible to write down if you don't say 0 factorial is 1. It becomes something of an exceptional case. So that's what mathematicians found out a long time ago. So you should always know that 0 factorial is 1. So you have 1, and that's x over 2. The next one would be 2 factorial is 2. -1 to the first power means it's a negative. And 2 to the 3rd power is 8. 8 times 2 is 16, so it will be 1/16 of x cubed. And this one, 3 factorial is 3 times 2 times 1. 2 factorial, 2 to the 5. 2 to the 5 is 32. 32 times 2 will be 64. 64 times 6. So that's what you're going to get. So it will be 1 over 384 and x to the 5th power. Okay, so what is J1 of 2 using just the first 3 terms? Assuming that the next terms and the next terms will become much smaller than this. Actually, it's not really true. I think for J1 of 2, you probably need to go like at least 10 terms, and you need to use a calculator or a computer to do that. But I'm just asking you to use the first 3 because it's easier to calculate. So you have 2 over 2 minus 1 over 16, 2 to the 3rd power, plus 1 over 384 times 2 to the 5th power, so on and so on. This is 1, that's 8 over 16, which is minus 1/2. And then 32, well, actually, if you reduce this, it's going to be 1 over 12. So the approximate value would be over 12, what's that? 12 minus 6 plus 1. So that's going to be 7 over 12. That's the approximate value of J1 of 2.